All right, this is Honors Algebra 2 Pre-Calc. We are doing 4.8 in Pre-Calculus. This is basically the Trig word problem section. It's our second video in this section. So it's that time, game on word problems. So here's the big secret about word problems. If you hate word problems, stop caring so much about the words. So I'm pretty decent at math. I'm not amazing at it, but I'm better than probably your average person. And this is how I read most word problems. Blah, 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 equation, blah, 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 value they want. And that's the big one. What's the value they want? Once I have a basic idea of what the math is, then I can go back and read the word problem in a more discerning way for any of the tricky info, and it's less daunting. So why is this useful? Here's the logic. Let's say I tell you to go search your house until you find the thing, but you don't know what the thing is. Your search is going to seem pointless and impossible and overwhelming, right? Because you don't know. I just said go find the thing and you don't know what the thing is, and so that's going to be really frustrating. If instead I tell you specifically that I need you to search your house for something to keep my noggin warm, well, you're probably going to go in your house and grab me a hat and come right back out. No big deal, right? Because you had more information about what I was looking for, then the search suddenly wasn't so hard. So if you're searching this huge word problem without any sense of direction, that's akin to searching your house for some random thing. You have no idea what you're looking for, and so your brain is totally over it. If you skim through the problem and try to find what value they're asking for, right? Same as when I asked, I want a thing to warm my head, right? I want a thing to warm my noggin. Then you can go back through the word problem, aka your house, and try to find the solution, meaning that dope hat with the ear flaps. What I'm saying is that most word problems actually aren't that tricky. People just are terrible at how to approach them effectively. So one more hint, if there's not an equation in the problem. So if there's an equation, they're probably just asking you to use the equation in some way. But since this is the trig section, it's probably not going to be equations. If there's not an equation and you aren't provided with a diagram, you probably want to see if you can draw what's happening, especially when we talk about these trig problems, because it's usually some sort of a triangular picture. And drawing the diagram is going to help a lot. Labeling the stuff that you know and labeling the stuff you want with a variable is huge. So we're going to walk through a bunch of these problems. Some of them will come with diagrams, some of them will not. All right, so let's get started. So we're going to solve the problem. If we're approximating anything, we're going to round or truncate to the thousands place. So the sun is 20 degrees above the horizon. Find the length of a shadow cast by a building that is 600 feet tall. Okay, so here's what's happening. Here's the sun, okay, and there's a building. And oh, I never draw anything to scale, so I apologize in advance. So that we know the building is 600 feet tall, right? And we know that the sun is helping this building cast a shadow, right? Like this. Now, you can always assume the ground is perpendicular to the building until I start telling you otherwise, right? So here's what we know. The sun is 20 degrees up in the sky, and we are asked to find the length of the shadow that I'm going to call x. That's what we want. Once you realize this, you say, cool, I see that I have the opposite side. I see that I want the adjacent side. I'm going to use TOA, right? So tangent of 20 degrees equals the opposite, which was 600, over the adjacent, which is x. We've seen this a few times. To solve, I'm going to multiply the x over and get x tangent of 20 degrees equals 600. And then remember that tangent of 20 degrees is just a number. So I'm going to do 600 divided by the tangent of 20 degrees. So when I do that, 600 divided by the tangent of 22. Make sure you're in degree mode, but we already are because I was in the last video. I'm going to get that x is approximately 1648.486. And it was feet. So make sure if it's a word problem with units that you have units. All right, next problem. Height, a ladder 20 feet long leans against the side of a house. Find the height from the top of the ladder to the ground if the angle of elevation of the ladder is 80 degrees. So let's go ahead and draw this. So I have a house. I don't care that you draw, like, it doesn't have to look like a house. You can if you want. Look, it's a house. Yay. Okay, house. I don't really care. All right, so I have a house, right? There is a ladder leaning against the house, like this, right? The ladder is 20 feet long. And we know that the angle of the ladder, the angle of elevation, is 80 degrees, right? The question is, how high does this reach up the house? And I'm going to use h for height, right? From the top of the ladder down to the ground, right? So once I know that what I'm looking at is the hypotenuse and what seems to be the opposite side, right? That's opposite the 80. So I'm going to use so. So the sine of 80 degrees equals the opposite, which is h, over the hypotenuse, which is 20. I need to type into my calculator 20 sine of 80 degrees equals h. So 20 sine of 80 degrees, again I'm in degree mode, equals h. And I get that h is approximately 19.696 feet, probably, because the ladder was feet. There you go. All right. Next one, we're given a picture. Now that usually means the problem's a little harder. I'm going to be honest. If you're given a picture, then it's probably a little bit complicated. So, angle of depression. A global positioning system, that's GPS, in case you were wondering what GPS stands for, satellite, orbits 12,500 miles above Earth's surface. Find the angle of depression from the satellite to the horizon, assuming the radius of the Earth is 4,000 miles. Okay, so here's the trick. What we're being asked to find is we're being asked to find this angle of depression right here. So you do need a little piece of outside information that I'm not sure if you know. So the piece of outside information you're going to need is that the tangent line, right, the tangent line to a circle, which is, this is a circular orbit. I mean, it's questionable. It might actually be an elliptical orbit. We're going to assume it's a circle, is perpendicular to the radius of that orbit. So this thing here is a 90-degree angle. So essentially what I'm going to have to do, right, to find this angle of depression is I'm going to have to find this mystery angle and then say that whatever this mystery angle is, and I'm going to call this theta, right, and I'll call the angle of depression x, I'm going to have to say that x, the thing I want, plus theta is 90 degrees. So basically, once I find theta, I do 90 minus theta. That's what I'm going to have to do. So let's look at this triangle. This triangle, right, so here's the thing I called theta, right, this is a 4,000. And then this is tricky because it's not actually a 12,500, because this is also the radius of the Earth, right? So this is actually a 4,000 here. So this is a 16,500. And what I need to do is find theta. So I say, oh, this is the side that is opposite theta. This is definitely the hypotenuse because they put a right angle right here, right? This is the hypotenuse over here. And this is the opposite. So I'm using so, right? I saw opposite and hypotenuse. So the sine of the thing I called theta is the opposite, 4,000, over the hypotenuse, which is the 16,500. So theta is going to be sine inverse of that value. And since that's an acute angle, that's going to fall in quadrant 1. I don't have to worry about anything weird happening with my sine inverse. So second sine, right, is sine inverse, and it's going to be a 4,000 divided by 16,500. Enter. Now I'm going to store that as alpha A. So I get that theta is approximately 14.029 dot 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 dot, and I'm going to store that as A, right? I know the angle I want, right? The angle of depression, the thing that I labeled as x, is going to be 90 minus that theta, which means it's going to be approximately, and so I'm going to go ahead and do 90 minus alpha A, and I'm going to get that the angle of depression is approximately 75.970 degrees. So again, if you're given the diagram, it's probably a more complicated problem, and that's a thing to be mindful of. All right, speaking of which, all right, so here's one where we're not given the diagram, but we'll see if we can figure this out. The angle of elevation, all right, so an amateur radio operator erects a 75-foot vertical tower for an antenna. Find the angle of elevation to the top of the tower at a point on level ground 50 feet from its base. So there's a tower, right, tower. And 50 feet from the base of the tower, we're looking up at the thing, right? And we know that the tower is 75 feet tall. The question is, what's the angle of elevation? So theta is the thing I want. Well, I look at what values I have, and I see that this is the opposite side, and this is the side adjacent to theta, so I definitely want TOA. Once I know that, the tangent of the mystery angle theta is the opposite, 75 over the adjacent 50. So theta is going to be the inverse tangent of 75 over 50. And you'll notice that in all of these, we're using triangles, and in a triangle, all of the angles that are non-right, in a right triangle, the non-right angles have to be acute. So I don't have to worry about anything with regards to the output of arc-trig functions, because remember, all arc-trig functions work in quadrant 1, and acute angles live in quadrant 1. All right, so I get that theta is approximately 56.309 or 310, depending on if you round or truncate, and it is degrees, so make sure you write degrees. All right, moving on. While traveling across flat land, you notice a mountain directly in front of you. The angle of elevation to the peak is 2.5 degrees. After you drive 17 miles closer to the mountain, the angle of elevation is 9 degrees. Approximate the height of the mountain. So we've seen this one before, right? I told you that you might see it with King Kong or Godzilla or City Hall when I write it for you as a problem, but we've seen this one before. So you're driving, right? And way over here, there's some mountain, and I'm just going to use M for mountain. Okay, we use M for the mountain, right? And you look up from this parked position of your car at the mountain, right? You look up, and what you see is that it's a 2.5 degree angle of elevation, right? Then you drive 17 miles closer, right? So this is a distance of 17 miles. And from this new spot, you look up at the same mountaintop, and you see that the angle of elevation is now 9 degrees. Well, you have two right triangles here. So there's this mystery value I don't know, x. So the one right triangle is this red triangle right here, right? So the red triangle has an M and an X and a 9 degrees. The other triangle is the thing I'm going to draw in blue, this big outer right triangle, right? And it has measurements of 17 plus X and M and 2.5 degrees. So what I'm going to have to do is I'm basically going to do this like it's two separate problems at the beginning. I'm going to recognize that in both cases, the thing I know is the opposite and the adjacent. So for the blue triangle, I'm going to say that the tangent of 2.5 degrees is the opposite, M, over the adjacent 17 plus X, right? And I'm going to go ahead and multiply the 17 plus X over times tangent of 2.5 degrees equals M. I'm going to do the same thing in red, right? I'm going to say the tangent of 9 degrees equals M over X, right? So if I multiply the X over X, tangent of 9 degrees equals M. And then this M and this M are the same. So what this does is it affords me the opportunity to make these the same equation. So I'm going to go ahead and distribute the 17 plus X, and I'm going to get 17 tangent 2.5 degrees plus X tangent of 2.5 degrees equals an X tangent of 9 degrees. And then I want to move all of my X's to one side, so I'm going to move this guy over. I'm going to get 17 tangent of 2.5 degrees equals X tangent of 9 degrees minus X tangent of 2.5 degrees. It is worth noting that you can't combine these because tangent of 9 and tangent of 2.5 are different values, right? If they were both tangent of 3, then you could deal with something, but tangent of 9 is a number and tangent of 2.5 is a different number, and they can't be combined. So if I factor out that X to solve for the only variable I have left, I factor out the X and I get tangent of 9 degrees minus tangent of 2.5 degrees, which I can then, that whole ugly number, divide it over and get that X is that 17 tangent of 2.5 degrees over, in parentheses, tangent of 9 degrees minus tangent of 2.5 degrees. Now that's X, and I could find a number for X, but X isn't the answer I want. So what I'm going to do is I'm then going to take the easier of the two equations, right? The easier equation. You could take either, but the easier equation is that M is X, so whatever I get here, times the tangent of 9 degrees. And that's how I'm going to get my M value and my approximate answer in miles. So let's go ahead and do that. So I'm going to type into the calculator 17 tangent of 2.5, close the tangent, close the numerator, divided by parentheses, tangent of 9, close the tangent, minus tangent of 2.5, close those and close the denominator and hit enter. So this is a 6.4697 da 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 da, and I can store that as A, right? Or I could honestly just multiply it in the next step by tangent of 9, right? Because I know that's what I'm going to have to do to it. And I get that this is a 1.024 or 5, depending on if you round or truncate, 4 or 5 miles. All right. And we saw a problem similar to this in maybe 4.3. We saw a problem similar to this in another section. All right. Solve the problem. So again, same thing, approximation might be required. A plane is observed approaching your home, and you assume that its speed is 550 miles per hour. the angle of elevation to the plane is 16 degrees at one time, and 1 minute later it is 57 degrees. Approximate the altitude of the plane. Okay, so here's your house, right? And we neglect the height of the observer, meaning that we don't worry that your eyeballs are like 5 feet off the ground, right? We pretend everyone's army crawling on the ground, and it's cool. If you were actually doing surveying, like people that actually measure heights of things, they have surveying equipment that accounts for the height of the observation. So if the surveyor, if the lens that's being used to like take a photograph of something when you're surveying, or if the laser beam that's shooting across a street to target some other thing when you're surveying distances, they account for that height. You can set the height on the actual tripod to make sure that it's accounted for. Obviously, we're not doing anything of that level here because it'd be weird. Anyway, so this is your house, right? Yay, that's you in your house. So a plane is flying towards your house. So here's a plane, and I apologize in advance for my inability to draw a plane. It's not going to look like a plane. It's cool. Okay, hey, it's a plane. Okay, so a plane's flying towards your house. You look up at the plane, right? You look up at this plane, and you realize that the angle of elevation that you're looking up is 16 degrees, right? But then the plane flies closer to you, right? It flies closer. And now when you look up, and again, I apologize in advance for the inability to draw a plane. Kind of looks like a plane. It's fine. Okay. So now when you look up, this angle of elevation, the whole blue angle, is a 57 degrees. Here's what you know. You know that the plane was traveling 550 miles per hour, right? So, and that this distance was a distance of 1 minute later. So 550 miles in 60 minutes, right, means that if you go ahead and do 550 divided by 60, right, and I'm going to math frack it because it's going to bother me that that's a repeating decimal. You get that this is, oh, well, it could have, I thought maybe it would simplify nicer. You get 55 over 6 miles in a single minute, right? So this is how far this thing travels in a single minute. This number is a 55 over 6 miles, right? Because this is how fast it travels in 60 minutes. So in 1 minute, it travels 55 over 6 miles. So that's the number on this side. So now if we look at this, basically what's happening here is there are two triangles, right? So there's, sorry, wrong color. There's this big red one, right? The plane has a height. We use A for altitude, right? And then there's this blue one, right? There's this blue one, but the height is still also A because the plane is just flying at a constant height over your head. So we want to find A, and the only thing we know, so I can call this side X, but I know that this piece is 55, 6. So I'm pretty sure what's happening is we have two triangles. We have a blue triangle that looks like this, A and X, and a 52 degrees. 52? I think it's 57. Hang on. My own handwriting's kind of bad. 57. My bad. That's a 7. It kind of looked like a 2. All right. And then we have this other angle, right? Or we have this other triangle where the side is the entirety of X plus a 55 over 6, right? This is still an A, and this is a 16 degrees. So this is the same basic problem. I'm going to want to set up tangent, right? I'm going to set up a blue tangent problem. So the tangent of 57 degrees equals A over X. So X tangent of 57 degrees is my A, right? In red, again, I'm going to set up a tangent equation. So tangent of 16 degrees equals A over this X plus 55 over 6, right? If I multiply over, I get X plus 55 over 6 times tangent of 16 degrees equals A. Well, notice they're the same A, right? So I can set, since this A is the same as this A, I can say that this is X tangent of 57 degrees equals, and when I distribute this here, I'm going to get an X tangent of 16 degrees plus a 55 over 6 tangent of 16 degrees, right? I'm going to move all the x's to one side, so I'm going to subtract this guy over and get X tangent of 57 degrees minus X tangent of 16 degrees equals a 55 over 6 tangent of 16 degrees. I'm going to factor out the x because that's what I'm trying to solve for. So I factor out the x and I get a tangent of 57 degrees minus tangent of 16. Again, a reminder, they cannot be combined in any way. And that's the big ugly number I'm going to have to divide by. So I'm going to get that x is 55 over 6 times a tangent of 16 degrees over this entire ugly tangent of 57 degrees minus tangent of 16 degrees, right? And even after I find that, right, I'm then going to use the easier equation, which in this case I think was the blue one. Sorry, my bad. I'm going to use the easier equation, which was the blue one. after I find x, I'm going to say that a, not h, was x tangent of 57 degrees. So whatever I find for x, right, whatever I find for x, that number is going to go here, and that'll give me an approximate value for h. So let's go ahead and type that in. So 55 over 6, tangent of 16 degrees, divided by, and then the whole denominator has to be in parentheses because it is a binomial. The top is a monomial, so it didn't have to be. The bottom pretty much always has to be in parentheses, even if it's a monomial, because otherwise it does multiplication before it does division sometimes because it works left to right. Multiplication and division are on the same level. Okay, so let's check. 55 over 6. And if you want to be extra safe, you can insert parentheses in your numerator and say, hey, the whole numerator's grouped together. You really don't have to, but if it's making you at all feel uneasy, you can. So there's the numerator all together, there's the denominator all together, and hit enter, right? So I get that this one is a 2.0975 da-da-da-da-da, and I can either store it as something, right? I don't know, I might pick B because I already used A here, I don't care. Or honestly, I can just say multiply by, because that's the answer. It'll be the full output, tangent of 57. And then I can hit enter, and I get that this should be a 3.229 or 30, and I believe this one was also measured in miles. All right, moving on. Okay, so let's talk bearings for a sec. So bearings are often used in navigation. There are two basic ways to write bearings. One is to start facing one of the cardinal directions, right? So for instance, start facing north. Tell me to turn 50 degrees towards the west, and that would look like this. So north, 50 degrees west, means face north first, turn in the west direction, 50 degrees. The other way is if you don't see it with direction, degrees, direction, you might see it where they just say a bearing of 30 degrees. Whenever you see that, it always means clockwise from north. So start north, go clockwise. So essentially it's the same as north 30 degrees east. I'm just throwing that out there because we are going to see bearings in some problems, and it's hard if you don't know what they are. All right, so this is a particularly hard problem, so I wanted to make it an example rather than a practice problem, just so we'd walk through it first. So a surveyor wishes to find the distance across a swamp, see the figure. So essentially the surveyor wants to find BA, right? So when we hear distance across the swamp, they probably want BA, but let's go ahead and walk through the whole thing. The bearing from A to B is north 32 degrees west. So what I'm going to do, what I would normally do is I would draw these on the corners, right? I'd draw one of these at C, I'd draw one of these just at B, and I draw one at A. But since I'm on a computer and I have the luxury of not drawing it by hand, it's going to be a lot easier if I just plop one on here. So I'm going to go ahead and put these little bearing cardinal direction things on each one of those angles. And again, I would do it by hand if I were doing this on a board, but since I'm here, why not? Okay, so the bearing from A to B, so that's from here to here, right, is north 32 degrees west. So what's that saying is this is a 32 degrees, okay? That's 32 degrees. That also gives me some other information, because see how this is a right angle here? So that means that this angle, right, the whole thing has to be a 90-degree angle. So if that's a 32, 90 minus 32 should give me a 58. So this angle right here should be a 58 degrees, and we'll talk more about other stuff in a sec, but that's because this entire angle is a 90, right, and I know this piece was a 32. The surveyor walks 50 meters, and they labeled that for me, right, from A to C. The bearing from C to B, so here's C to B, is north 68 degrees west. So that means this is a 68. Now what that means is if that's a 68, you can see that this is a 90-degree angle, right? North and west make a 90-degree angle. So if that's 68, you can actually find this mystery angle in here, right? Again, 90-degree angle, so you can say 90 minus 68 should give me a 22. So this angle right here is a 22, right? So again, it's a 22. I know it's a little bit hard to see. Okay, 22. All right, so we're asked to find A, the bearing from A to C. Well, we can actually find the bearing from A to C. I actually found that already, right? I found the bearing from A to C almost instantly. So the answer to A is north, turn 58 degrees to the east. So north, 58 degrees to the east. Okay, so that takes care of answer A. And then find the distance from A to B. So the trick is to find the distance from A to B, I really need an angle, right? Because if you look at this triangle, what I've got here is I've got a triangle where I want this side, this is the thing they're asking me to find, and I know this is 50. I need one of these angles, right? So there's a couple different ways to get this angle, right? the biggest thing here, right, is that I can actually figure out that if this, okay, so this line, right, is a transversal between two parallel lines, right? Oh, that's not quite the one I wanted, but you get the gist. Okay, so I mean, it does work. So it's a transversal between two parallel lines. And see how this is north-south, it makes a right angle with the east-west. So I know that if this is 58 right here, right, if this is 58, then I can subtract and figure out that this piece, right, this piece has to be a 32, which means this piece here, alternate interior angles, is also a 32. So this angle right here is the 22 plus the 32, which makes it a 54. Once I know that that's a 54, now I can say this is the opposite side, this is the adjacent side, I just need tangent. So tangent of 54 degrees is the x I want over a 50. So I'm going to type in my calculator 50 tangent of 54 degrees as my x, and I'm going to get that x is approximately 50 tangent of 54 degrees, a 68.819 meters, because the problem had meters. So the answer is 68.819 meters. Again, this one's really tricky because you kind of have to write all over it and figure out which angles sum to 90 degrees, and those little bearing symbols in the corner kind of help. All right, let's go ahead and keep working through some problems. All right, so we're going to do one more problem in this video, and I have to admit that the first time I saw this problem, it stumped me a little, and then once you see it, sometimes it's much, much easier. So let's go ahead and walk through this. So a ship leaves a port at noon and heads due west. So west is this way, right, which must mean that this is where we're starting, right? It also makes sense because they made start be A. So this thing goes due west until 2 o'clock at a speed of 20 knots, or that's 20 nautical miles per hour. So over 2 hours, from noon to 2, this thing went 40 nautical miles, right? So 40 nautical miles. At 2 p.m., which happens right here at B, the ship changes course to go north, which is north 54 degrees west, would be this, that's why this 54 is here. And it does that until 3 p.m., which is 1 hour. So that'll be another 20 nautical miles. So we have two questions. What is the bearing and distance at this beginning? So the bearing, right? So we want, what is the, if I grab this for a sec, the question is, what is the bearing, the original bearing to the final location that we get at 3 p.m.? And so that's question one, right? So question one is, what's the bearing, right? And question two is, what's the distance from the original point to where the ship is at the end of that time? And that would be C, right? That would be this value. So the two things I need to find are this angle that I'm going to call lowercase, I don't want to call it lowercase a, we'll call it capital A, because that's the, so the two things I need to find are angle A and lowercase c. That's what I'm being asked to find. So now let's think about how we can do this. I notice that there are two right triangles, right? There's this little one, right, here. So I seem to have a triangle that looks like this, lowercase b, lowercase d, and then a 20 for the hypotenuse, right? And then I don't actually know this angle, but I know that B, which is north-south, and this line, which is east-west, they make a 90-degree angle. So I can figure out that this angle is a 36 degrees by doing 90 minus the 54 degrees. So I know that's 36. The other triangle that I see that I have is this really big triangle over here, right? And that's the one I'm going to need to get some of the answers, right? But the trick here, right, so I want to find angle A, and again, ignore my terrible drawing, so I want to find angle A, and I want to find side C. What I know about this side is it seems to be D plus the 40 nautical miles, right, because there's D to get to that dotted line, and then 40 nautical miles to get to here. And then there's still B. So I don't know very much about this triangle, right? And my mistake originally was that I was frustrated. I didn't have, I mean, I literally have no information about the green triangle, and yet these are the things I want, right? And I have no information. So I started to get a little frustrated. And then I realized that I have a ton of information about this black triangle over here, tons of information. So I realized that if I found B and D, right, if I use this triangle to get B and D, well, then I have a ton of information about the green triangle, right? So what I'm going to do is I'm going to set up B would be the opposite side over the hypotenuse of 20. So B over 20 is the sine of 36 degrees. Well, that means I can get that B is just the sine of, 20 times the sine of 36 degrees. It's better to put the 20 in the front. So 20 sine of 36 degrees. right? So that's my B, and I can type it in and get a number, or I can recognize that now I know B, right? And that's it. That's all I needed. Similarly, D, right? D is the adjacent side, so D over 20 should be the cosine of 36 degrees, right? So I get that D is just 20 cosine of 36 degrees. And again, I could get a value for that, or I could say, oh, look, hey, convenient, that's D, right? Well, now I have a triangle that I actually know a ton of stuff about. So now when we look at that big green triangle, what's happening here now, and again, ignore my inability to draw, right? I really want angle A, and I really need side C. Well, I now know that this entire side is D plus 40. So that's a 20 cosine of 36 degrees plus a 40, right? This whole thing, this is this whole side, right? And that this side is B, which was 20 sine of 36 degrees. Well, that means that I have two pretty easy ways to find angles, right? I can say that angle A, this is the side opposite angle A. This is the side adjacent to angle A. So tangent of angle A should be the opposite, which is 20 sine of 36 degrees, divided by the adjacent, which is 20 cosine of 36 degrees plus 40, right? The whole thing in parentheses. So I can find that A is the inverse tangent of that ugly chunk of values, right? Of that whole thing. So it's up to you. You might want to find a value for this, right? You might want to find that value first. It really doesn't matter. So you can type in inverse tangent and then type in this whole monstrosity. It's just a little bit complicated, right? The numerator is 20 sine of 36 degrees, close the numerator, divided by, the denominator needs parentheses, 20 cosine of 36 degrees, close the cosine, plus a 40, close the denominator, and then close the arctan, right? And again, you could get rid of the arctan if you want, like, so I'm gonna type the whole thing in, so 20 sine of 36 degrees over 20 cosine of 36 degrees plus 40, right? And I'm going to get that A, right, when I hit enter. A is approximately an 11.818 or 9 degrees, but that's not actually my answer about the bearing, right? So usually a bearing is a north-south direction to an east-west direction. So I actually want this other angle for the bearing, right? I want the other angle. Now you could technically write this bearing as west, so it wouldn't be wrong. You could say, hey, that's west, 11.818 or 9 degrees to the north. It's unconventional, but you could say it. What would be more likely, or more likely, you would take 90 minus that angle you got, right? So I'm just going to subtract 90 and know it came out negative. That would be a 78.181 degrees, right? So the more likely answer would be north, 78.181 degrees west, right? That's the more likely answer. And then in terms of finding C, honestly, the easiest way to find C is probably Pythagorean theorem, right? So then the last thing I need to find is C, but I know what these two sides are. So I'm going to be a little bit lazy. So I'm actually going to use B and D, right? I'm going to store this as B. I'm going to store this as D, and it just makes my life a little easier. So 20 sine of 36, and I'm going to store that as alpha B, right? And then 20 cosine of 36 plus a 40, and I'm going to store that as alpha D, right? And then I say, oh, cool, this thing, C squared, should be B squared plus D squared. So C is the square root of B squared plus D squared, and I know it's positive because it's a distance, and that's a scalar. So square root of alpha B squared plus alpha D squared, close that, and there's my answer. So, so I'm going to get that C is approximately 57.397, it's a 7, nautical miles, right? And again, I have to make sure I have degrees. So once I know B and D, I can find pretty much, pretty easily, I can find the other stuff I need to find. And again, that stumped me a little bit at the beginning, and I think sometimes you'll find that. Like sometimes you read a problem and you draw the triangle and you just get stuck, and that's okay. But, you know, hopefully you puzzle through it, and occasionally on a problem you won't, but that's all right.